Is anyone there? I got my speakers on this time.
Yeah, we're here.
Okay. Okay. And let me get set up a little bit. Okay. Okay. Sorry I didn't have my speakers on last time. I know that I guess there was people trying to ask me questions. I was wondering why everyone was so quiet. So I'm sorry I didn't notice the little speaker thing over here. So I got my speaker on this time. So if you have a question, just try to interrupt me at any time. Yeah, and I'll try to answer any questions. So what we're going to do today is there's your new homework assignment is up there. Okay, so your new homework assignment is up there. So this is the page that describes it. This is the zip file. And what we're going to do is first we're going to review what we talked about on Monday. Demand paging, not the translation look-aside buffer, but we're going to go back over demand paging because this homework assignment is a good example of how you can watch demand paging take place. So it lets you run a program and watch what happens. So first we're going to review demand paging, then we'll go over the homework assignment. Okay, so let's see. So before going over the homework assignment, want to go back through the details of demand paging. So I downloaded this, the examples we want to talk about are in this folder. Should create a higher link, this one down here, Windows Virtual Memory. You should download this over again if you haven't downloaded it in a week or so, because I've added some more notes to it. So it's worth like downloading this thing maybe every once a week because I've been adding things to it. So I added things to it last night. That's what we'll look at today, some stuff about demand paging. So you might want to download that zip file again because it's got some new things in it. Okay, so if I open that zip file and go to the folder on paging, I wrote some notes on demand paging. So I wrote, our textbook doesn't really explain demand paging. They do, but in our textbook, it's a little bit ahead. They're going to talk about demand. Sorry, the textbook. If you go to the textbook website, the actual stuff about demand paging is on this swapping, but demand paging doesn't need swapping. That's one of the things I want to emphasize is demand paging. There's really three versions of paging: plain, simple paging, demand paging, and swapping. So swapping is really the third version, but he blends demand paging in with the swapping. So we're going to keep them separate. We've talked about so sometimes called pure paging or just simple paging, then demand paging, then swapping paging. Okay. So he talks about demand paging, but it's mixed into this chapter, which we haven't actually got to yet. Okay. So, and demand paging by itself is much simpler than swapping paging. So I think it's worth talking about because he's blending a whole bunch of ideas together in one, but you can separate those ideas and it becomes a little bit easier to understand them if you digest them in steps. So demand paging is something you can talk about before talking about swapping. Okay, so here's a definition of demand paging. Okay, and what we're going to do is we're going to go through this description of it and then draw some pictures. Okay, actually, let me get ready to draw pictures. Okay. Okay. Now, what we want to do is, well, actually, let me describe it by drawing a picture, and then we'll go through and read what this says. So here's what our setup's going to be. We're going to be running a process. Let me see if I get this set up. We want to have a virtual memory space. Okay. So here's a virtual memory space for our process, and then we're going to have a physical memory space. And we're going to have a page table in between. And we're also going to, so let me label these. We're going to have the virtual memory space, the physical memory space, and the page table. So you just use abbreviations: virtual memory space, page table, physical memory space. Then what we need to add to this picture that we didn't need before was the hard drive. So this box is going to represent the computer's disk drive. Yeah, or if you want, in general, mass storage. Because these days it doesn't have to be a disk drive. It could be a solid state drive. So it's someplace where you have fast mass storage. Okay. Now, virtual memory is divided up into pages. So I'm going to give this guy some pages. Okay. So memory is divided up into pages. And physical memory is divided up in the same size, but not necessarily the same number of pages. So I drew physical memory bigger because I wanted to have a different number of pages. Okay, so here's the page frames in physical memory. Pages over here and page frames over here. So you have to remember to keep the terminology. Over here are pages. Oops. Pages. And over here are page frames. Okay. Now, when you want to run a program, the program starts off. Here's the key idea. We're gonna go through the whole process of what it means to load a program. And demand paging describes a process for loading the programs that's not an obvious process. It's a little bit different than what you might think. Okay, so the program starts off on the hard drive as an exe file. So, oops. So here's what I'm going to do. I'm going to imagine the program on the hard drive. So here's the exe file on the hard drive. Okay, so this is the exe file, and it's divided up into things that are the same size as the pages, but they're called sectors. Okay, so over here we have sectors. They're the same size as pages. Okay, the hard drive is divided into sectors, and this guy is the exe file that we want to run. Okay. All right. So we have an exe file that needs 3 pages of memory. Okay, and we're going to load that exe file into virtual memory, and eventually it's actually really going to be loaded into physical memory. Yeah, we have virtual memory and physical memory, and when we load the program, we really load it into physical memory, but we also think of it as being loaded into virtual memory. Okay, now suppose that the compiler wrote this thing here. Suppose the compiler decided that this is going to be, oh, let me add some more notation. This is page 0, page 1, page 2, page 3, page 4, and page 5. And over here, we have page frames. Okay, go through page 0, page frame 0, page frame 1, page frame 2, 3, 4, 5, 6. Okay. The compiler wrote the EXE file. So the compiler decides each sector represents a part of your program. And the compiler decides, for example, that this should be, let's make this page 3. So this is going to get loaded into virtual memory page 3. And this sector is actually representing virtual page 4. And let's suppose that this sector represents virtual page 1. Okay? So this is an EXE file on the hard drive, and the EXE file starts here, ends here, but the pages don't have to be in any real order. Okay, so maybe the compiler decided that this sector will be loaded into page 3, this sector will be loaded into page 4, this sector will be loaded into page 1. Okay, so that means now we can start filling in our page table. Okay, the page table, let's see, we have 1, 2, 3, 4, 5, 6 pages. So the page table should have 6 rows to it. Okay, so I'm going to see if I can get 6 rows in this guy. 1. So the page table needs 6 rows. 0, 1, 2, 3, 4, 5. Okay. Now, in a classic paging system, when it's time to run this program, oh, I need to do one more thing. The page table is divided up into there's going to be 2 bits over here on the page table. We're going to have a page table with a valid bit and another bit called the present bit. So I'm going to put 2 bits over here. Whoops, I lost my. Okay, so this part of the page table is the page frame number. Okay, and this column is going to be a bit that we call the valid bit, which we've talked about. And then there's this bit that we mentioned a little bit about the other day. This other bit is going to be called P for present. Okay, so the page table is a page frame number, then a valid bit and a present bit. Okay, so this program is ready to run. The classic way of doing paging is that the program is loaded into memory all at once. So when you decide to run this program, the operating system goes to this EXE file, sees that it has 3 pages. Okay, so this is let's do the regular paging first, then we'll do demand paging. So with regular paging, all at once this program is loaded. So this stuff here is copied into here. Okay, I'll just put XXX. So this stuff here is copied into there. This stuff here is copied into here. And this stuff here is copied into here. Okay, so, but actually, it's not really copied into there. We think of it as being represented in there, but what really happens is the operating system goes over here to the page table, and it says, okay, page 0 is not valid because the program is not using it. Page 1 is valid. And now we're going to put, now the operating system says pick a page frame to put page 1 in. So we'll put page 1, say, in this page, number 4 over here. So we'll put page 1 in 4. Okay, so that means that page 1, which is ZZZ, the ZZZ is really over here. This stuff here is copied over into here. Okay. Okay. Then the operating system looks and says, okay, page 2 is not even in use, so it's not a valid page. Then page 3, it's being used. Okay, we have to decide where to put it. So let's put page 3 over here, say, in page 1. So over here, we put the XXX. The XXX is copied into here. Okay, and then page 4 is, oh, and page 1 has to be marked valid. Okay, page 4 is also valid. Okay, page 5 is going to be invalid. And let's put page 5, see, no, page 4, which is this one here. Page 4, let's put it over here in 3. Okay, so the YYY goes here, and this one is 3. Okay, so what happened here was this doesn't exist. The virtual memory really doesn't exist. So when it became time to run this program, the operating system looked on the hard drive, saw 3 sectors. So that means there's 3 pages. It sees that this is sector 3, which means it's page table entry 3, okay? And it decides where to put it. So the operating system says, okay, I'm going to take this sector and copied it to page frame 1. So then it puts into the page table in entry 3 in the page table, it puts the page frame number and it says that this guy is valid. Okay, then it goes to this sector, and the compiler told it this is sector 4. So this sector will go into page table entry 4. The operating system decides where it should go in memory. The operating system decided it was going to go over here in page frame 3. So it put a 3 here. It copied that content into there, okay? And then it marked it as present. Then the operating system said, I got to copy this guy into memory. So this one is actually page 1. So it goes into this entry in the page table. The operating system decides where to put it in physical memory. Oh, let's see, 1, 2. Oh, darn it. Okay, this was supposed to have been, did I mess up the numbering? Let's see. I can erase that 4. That was really supposed to be a 5 there. Okay, so let's see. Let's see. So virtual page 1 is in, this was supposed to have been a 5 here. Okay, so that one was supposed to have been a 5. Okay, right. All right, so 3 pages there's 3 valid pages and all the other pages are marked invalid. So there's 3 valid pages and 3 invalid pages. So this is paging. This all happens at once. Notice I haven't used the present bit. The present bit's going to be needed when we do demand paging. Okay, so this all happens at once. Okay, then once the program is loaded into physical memory, the program counter can be pointed at to wherever the start of the program is, and the program can start executing. When the program's executing in virtual memory, all its pages are loaded into physical memory and the program just chugs along. Now, it could be that one of these pages never gets touched. The problem with this is maybe this page here never actually gets touched for some reason. Maybe it holds some routines that only are handled in an emergency. So that page is in physical memory, but maybe it actually never gets used. Okay, so people realized many years ago that they ought to be able to do this a little bit better. They decided that they should only load pages in the physical memory when they're needed. So when they're demanded, when the running program says, I need this page, then you load the page. So let's go back and let's go back to the start where we're going to run this program, okay? And what I'm going to do is I'm going to erase everything in the page table. And we're going to go through the process again in the demand paging way of doing things, okay? And actually, I won't erase everything. We'll just, here's what start. When this program is going to run, here's what the operating system does in a demand paging system. It says here, oh, this program's got 3 sectors, which means it needs 3 pages. Okay. So the operating system says, well, it looks at what the compiler told it. The compiler said that the first sector is page 3. So that's going to be valid. But at this point, the operating system doesn't know if it's going to be needed or not. So the operating system says, well, page 3 is valid, but it's not present yet. We haven't allocated any page to it because we don't know if we really need it or not. So now we're going to start using the present bit. Then this is left, well, this has just got garbage in it now. There's just garbage in here. It's a valid page, but it isn't present. Same thing with 4. It's valid, but not present because nothing's present yet. We haven't actually executed anything, so we don't know, okay? And then page 1, it's also not present. It's valid, but not present. And these other pages that are invalid, we're going to mark them as not present, and they'll just stay not present because they're never going to get used, okay? So this is what things look like. Oh, and then I should erase what's in the virtual memory space because nothing's been put in physical memories yet. So I can erase what's in physical memory space. Nothing's there yet. So this is what a program looks like when it's loaded. At this point, from the operating system's point of view, this program has been loaded. The operating system read the EXE file on the hard drive. The operating system noted that the EXE drive represents 3 pages. Okay, so the EXE drive, the operating system realizes that there's 3 pages, pages 3, 4, and 1. They're marked as valid pages, but the operating system doesn't know which one of these are actually going to get used, so it doesn't actually try to load any of them. Okay, so this is what the program looks like, okay, when it's about to start up. Now, let's suppose that this is actually the code. Let's suppose over here that this is actually the code. This is the main method. Okay, so this is where the program would start running. Okay, so now the program counter is put into the CPU, and the CPU accesses this page because the first thing the program does when it runs is access main. Okay, so as soon as the program accesses main, the translation mechanism will say these addresses are in page 3. Goes over here to the page table and says it's a valid thing, but it's not present. So now we have to ask, so now the CPU tells the operating system using an interrupt, please load this page for me because I need it right now. So now the demand paging part of it steps in. Okay, the operating system comes in, says, oh, we need to find a physical page to hold 3. So what we're going to do now, we're going to copy 3. Let's see, I'll copy it. I'll just put it over here. So we'll put XXX, which is main, over here in page 4. So 3 will get loaded into 4. Now we say, okay, now it's present because we've decided where it goes. So we'll change this bit from a 0 to a 1. The program just, we say, paged in that page there. When the program accessed that page, it paged it in. Sometimes it's called a page fault because the operating system had to step in and copy this stuff over into here for us. It had to copy this stuff over into here and then denote in the page table that now page 3 of virtual memory is sitting in page frame 4. It's valid and present. Okay. Now the program is executing in main a little bit. Now let's suppose that this is the stack over here. Suppose this ring represents the stack. Okay. At some point, the program touches the stack. Okay. When the program touches the stack, the address in the stack is going to get translated over here to that page table entry. But then the CPU realizes that that page is valid, so it's okay, but it's not present. So the CPU has to interrupt the operating system and say, please load another page for me. Okay. So the operating system now says, okay, I have to load another page. This is going to be, which one was that? Oh, that's this one here. This sector here has to be loaded in memory somewhere. So the operating system picks a frame. I'll put it over here. So this is going to be ZZZ, which is the stack. And so that's going to go in page frame 2. Okay, so this one becomes page frame 2. Page 1 is now translated to page frame 2. I can now mark this as present. So that's now present. Okay. And now the main method can access its stack all at once. So now the program will just keep chugging along, accessing the stack, because now the main method's in memory and the stack is in memory. Now, if at some point, now let's suppose this one here is the heap. At some point, the program may decide that it needs to use the heap. The first time the program accesses the heap, the address in the heap goes to this page table entry. Okay. That page table entry is not present, so that's a page fault. The CPU has to interrupt the operating system and say, please load a page for me. Okay. So now the operating system has to find a page frame. So let's suppose it picks this one here. So it decides it's going to put YYY, which is the heap, over here. Okay. So now it says, okay, page frame 4 is page 4 is page frame 1, and it has to denote that as present. So now it changes the present bit to 1. And now the whole program has been loaded into memory. But it's been loaded into memory only when it was asked for. Only when a page got asked for was a page loaded into memory. Okay, so the operating system, remember, notice that the operating system had to keep track of which EXE file. Part of this process is keeping track of where the EXE file for it is on the hard drive. Okay, so that every time when you're running this process and it finds a not present page, the operating system can then go back to the EXE file and get what it needs. Okay, and it can get what it needs from the EXE file, copy it into the into a page frame, mark the appropriate page as present. Okay, all right. So we have pages, page frames, and sectors, all the same size. Pages are virtual; they don't really exist. They're in the virtual memory space. Sectors exist on the hard drive. Page frames exist in physical memory. Okay, so it's really important that all of these are the same size. On modern computers, they're all 4 kilobytes. The sectors, the pages, and the page frames are all 4 kilobytes, so that you can very easily copy from one to the other. So you can copy a sector to the hard drive. You can copy a sector into a page frame. They fit exactly. Okay, all right. So, let's see. Let me save this before I lose it. Okay. All right. Now, there's a little bit more to this. There's here's another thing that can happen. This program, we said that the compiler wrote it to have three pages. So the compiler decided this program has 3 pages. So there's it running in 3 pages. Now, suppose the program needs more memory while it's running. Okay. There's really no, this is actually kind of common. Let me show you an example. Let me call up Task Manager. Okay. Let me look at my memory. There's my memory. There's the amount of memory my computer is using. Okay. Now I'm going to go over here to TextPad. I'm going to do something funny. I'm going to have TextPad load a huge file I happen to have on this computer. Okay, so let me go find it. Let's see. This file here is 2.5 gigabytes. Now TextPad is about to be asked to open a 2.5 gigabyte file. You can see, oh, it's 2.1 gigabytes. That file's 2.25 gigabytes. Now, when you open a file in an editor, it loads it into memory so that you can process it. TextPad has no idea that it's about to be asked to load 2.25 gigabytes of memory. So what TextPad's about to do is start telling the operating system, I need more pages, I need more pages, I need more pages. Now watch that happen. Okay. Notice that TextPad's working. See how my computer is allocating memory like crazy. See over here, you can see that the computer just allocated 2 gigabytes of memory to TextPad. So TextPad has this whole file in memory, and you can do interesting things with it. You could search this file. Okay. Right now, TextPad is searching. The file is really in memory. TextPad is now searching 2.25 gigabytes of text for the word aardvark. It's going to find about 20 instances of aardvark. It takes it about 30 seconds to search there. See, it's just found aardvarks. Okay. TextPad is actually amazing. This is why I use TextPad a lot. It's an amazing editor. Some editors cannot do this. There are editors out there that you can't just load 2 gigabytes into them and say, okay, search the file for me. TextPad is known to be one of the better editors for that purpose. But you can see from our point of view, what's interesting is that TextPad on demand asks the operating system, I need more memory, and the operating system gave it. Now, when I close that file, TextPad's going to be probably, I don't know if, we'll see if TextPad gives up the memory that it was just given. Okay, so close the file. Yep, and then TextPad said to the operating system, I'm done with this memory. Now, TextPad's still running, but it asked the operating system for memory on demand, and then when I closed the huge file, it gave up the memory on demand. So let's think about in our model over here, how we would actually do something like that. Okay, so suppose this is TextPad and it needs more memory. Okay, and this is what you're going to be doing in your homework assignment. You're going to see what functions TextPad called to do those things. Okay, so you're going to write code that does what TextPad had to do. Over here, the idea would be that this program just tells the operating system, I want another page. Now, TextPad decides which one of these it wants to load into. So suppose TextPad says that I want data on my page 2. So the function is called memory or virtual alloc. Okay, so we'll see in a little while that the function that you call in Windows is called virtual alloc. So when this program is running, it decides that it wants to load data into that page. Okay, so it calls the operating system saying, I want to load data into this page. So the operating system says, okay, I'll make your page 2 valid. Okay, I'll make your page 2 a valid page. And then the operating system is lazy. It doesn't do any more than that. It says, okay, you want to load data in this page, so that page is going to be marked as valid. But the program maybe hasn't actually done anything with that memory yet. Maybe it hasn't actually tried to write anything into it. So the operating system just says, okay, that page is valid. And then the operating system says, well, we'll see what you do with it. Then maybe an instant later, the program starts writing data into that page. At that point, when it starts to write data into that page, the operating system says, oh, that thing is valid but not present. So now as a second step, the operating system says, now I have to, what we say, back that page with a page frame. So maybe the operating system goes over here and says, oh, I'll give you this page over here. So it's going to give, it's going to say, here's the page where you can put your data. It's page frame 5. So this will become page frame 5. And now that page is going to get marked as present. It was marked as valid. Now it's going to be marked as present. And now my program is grown in memory. Notice that that page is not represented in the EXE file. The program has dynamically grown itself a page. The new page down here is not part of the page that was part of the EXE file. It's data that the program is manipulating while it's running. And when the program terminates, that data will just disappear, unless that data gets saved to the hard drive, but the program would have to do that. The data will be, it's mostly just like TextPad opened a file, it read the data into pages. Maybe it manipulated the data, maybe it processed it. If it made changes to the data, it would need to write it back out to the hard drive to save it. Okay, so this is demand paging. One of the beauties of it is programs can grow. Similarly, the operating system can, at some point, maybe the operating system is done with that page. This program might at some point be done with that page. Just like when we closed our file and TextPad said, I don't need this memory anymore. As the program's running, the program could call another function saying, deallocate that page too. Okay, to deallocate that page too, the operating system will go over here and just mark that page as invalid. It might not even bother with the present bit, because if you're invalid, the present bit isn't even looked at. So the operating system can go over here and just mark that as invalid. It doesn't care about this. This number can stay here, that number can stay there, because when this page table entry is invalid, none of the data in it is valid. So to deallocate that page, you would just mark this thing as invalid. And then this page would become a free page. It would be free that anybody could use, like maybe these other pages are free. Okay, so that's stepping through the demand page idea. Programs are loaded into memory only as we say, touch the pages that they're using. Or a lot of times people use the word touch. It means you either read a page, write to a page, or try to execute the page. In general, people just say your program touched the page. When your program first touches a page, the page has to be switched from being not present to being present, which means the page needs to be copied into physical memory. You need to the operating system has to find a free page frame and mark it in your page table as you're using that page frame, and then load your data into the page frame. Now, if it's a dynamically allocated page like this data was, the operating system doesn't copy anything into the page frame. It's up to your program to put something in the page frame. So when they're pages from the EXE file, the operating system copies them into the page frames. If the page is a dynamically allocated page at runtime, the operating system will give you the page frame, it'll dedicate it to you, but it's up to your program to put data in the page frame. Because this page here is not represented by any sector in the EXE file. Okay, now everything we've just described is described in text over here. Okay, so this is the steps we just went through. See, when an EXE file is stored on a hard drive, it was put there by the compiler. So step 1 describes this idea here, that an EXE file sits on the hard drive and the compiler has decided which sectors are in use, which sectors represent which pages in virtual memory. So the EXE file has data in it that says this is page 3, this is page 4, this is page 1. Okay. When the EXE file is used to create a process, when you decide to run it, okay, the operating system will figure out which of these pages are in use, which pages over here are in use, and it'll mark those page table entries as valid but not present. Okay, so that's step 2. Mark pages as valid but not present. Okay, then steps 3, 4, 5, and 6 describe the different ways that you could page fault a page in. Okay. Oh, I didn't. There's some more page. Okay, let's actually add a little bit more to the page table entry. Okay, the page table entry. Remember, it includes some other bits. So let me add the 3. We talked about 3 other bits. Let me put them. Okay. Let me get this right. Okay. Let's add 3 bits to the page table entry. Barely give myself room here. The 3 bits are going to be the read, write, and execute bits. Okay, so now we have a, whoop, so there's now a read bit, a write bit, and an execute bit. Okay, now let's look at how those would be marked in here. Page 3 is the main method. That's executable. So page 3 should be marked as not readable. Well, yeah, not readable, not, whoops, not writable, but it should be marked as executable. Okay. On the other hand, the stack should be marked as readable, writable, and not executable. That's to prevent hackers from trying to use your stack, what's called stack smashing. The phrase for it is called stack smashing. So if you want to know what I'm talking, you just Google stack smashing. Okay. Stack smashing stack smashing just is this idea of trying to put code in your stack so that you can access it. Okay, there's a whole bunch of ways you can smash a stack. There's buffer overflows, one of them. There's a whole bunch of ways to do it. The prime way to prevent stack smashing is to make the stack pages not executable. Then if somebody puts code in your stack, there's no way it'll get executed. Okay, and then same with the heap. The heap should also be marked as readable, writable, and not executable. Now, we'll see that when you do your homework, when we talk about the homework assignment, when the program at runtime says, I want to create I need a new page frame, I need some more memory, one of the things you have to do is tell the operating system how the read, write, and execute bits should be set. So when this page got allocated, that was page 2. That's this one here. When it's allocated, we get to decide how these bits are set. So for example, maybe I want that to be read-only data. Well, let's see. Well, if it's read-only data, it has to be copied in there from somebody. Well, okay. Suppose you decide that you really want to play things dangerously, and you decide that page should be readable, writable, and executable. Maybe you're going to write your own code into there. Maybe you're a compiler or something, or you're just doing something funny, and you want that page to be readable, writable, and executable. You get to do that. Okay. Right. So, but when you ask the operating system to allocate a page for you, one of the things you have to tell the operating system is how to set the read, write, and execute bits. Notice that the valid bit and the present bit are controlled by the operating system. But programs actually control the read, write, and execute bits. So a program at any time can change the read, write, execute status of any of its pages. Okay, right? So over here, this number 3 here is when you page in an executable page. So when you page in an executable page, you set the executable bit. This one talks about paging in a stack page, so that would be read and writable. Okay, so there's these different steps describe the different ways you could page in. You could page something in as an executable page, or as a data page, or as on-demand paging. So 6 is the on-demand. That's this one here that was paged in not from the hard drive, but was just allocated to us at runtime. Okay, now, so that's a real pretty good detailed discussion of demand paging. Okay. Now let's go to look at the homework assignment. Okay, so let's go look at the homework assignment. The homework assignment lets us do these things. Lets us allocate pages and play with pages. Okay, so here's the folder for the homework assignment. As you might guess, you're going to have to read the description several times. It's not as long as the last homework assignment. This is not as hard a homework assignment as the last one. This is a easier homework assignment. You're going to write less code, and the code is actually fairly straightforward to write. Okay, what you're going to do is you're going to fill in this program here. I've sketched out. There's more explanation is here. In fact, this is quite a bit of the explanation is in this file rather than being in the web page. So instead of all of the information being in here, a good part of the information is in the EXE file, in the C file, because that's where you need it. You know, when you're writing the code, you'll want to be referencing this stuff up here. I've outlined code for you. You actually have to write 2 lines of code here, 2 lines of code here, 2 or 3 lines of code here, a couple lines of code here, a couple lines of code here, here, and here. So you have to write, you're actually going to write less than 20 lines of code because you've got 8 cases to take care of, and each case is at most, some of the cases are 1 line of code, some of them are 3 lines of code or 4 lines of code. So altogether, you're going to probably write about 20 lines of code for each of these cases, okay? And each of these cases do 1 memory operation, okay? So let's see what we mean by they each do a memory operation, okay? A memory operation is to do like what we were showing in this picture of asking for. A memory operation is when at runtime, a program asks for new pages, okay? These pages were put there automatically because they were in the EXE file. But this page was put in the program at runtime. So we're going to look at how a program at runtime can do memory operations. The memory operations are going to be to allocate a page, set its characteristics, like whether it's read, write, or execute, and to access the page, and to deallocate it. So essentially, we're going to allocate pages, touch the pages, then deallocate the pages. Okay. So we actually have 8 memory operations, but because it turns out that the details are always way more complicated than the overview is. But what we want to be able to do is allocate a page like we did here, access the page, then deallocate it. When we allocate it, we'll actually be putting it into the page table as valid but not present. So when you allocate a page, it'll be valid and not present. When you touch the page, it'll become present. And then we'll see how you can deallocate the page. So then it goes back to being invalid. So we want to be able to transition a page to being valid but not present, then touch it so it becomes valid and present. And then we want to deallocate it so it becomes invalid. Okay. In Windows speak, those operations, let's see. Okay. in Windows speak, those operations have the names reserve a region of memory, commit a block of memory, touch a page of memory. Then you can also do things. You can lock pages, unlock pages, create guard pages, decommit pages, and release pages. Okay, so this is allocating, and it takes 2 steps to allocate, reserve and commit. This is deallocating, which takes 2 steps, a decommit and a release. This is accessing a page. And these 3 have to do with changing the characteristics of the page. Those are manipulations of some of the bits in the page table entry. Those have to do with manipulating bits in the page table entry. Okay, so these 2 allocate a page, access a page, change a page's characteristics, and then deallocate a page. Okay. Okay, now these are some of the characteristics a page can have. These are manipulating page table entries. Pages can be read-only. That would mean that R is 1, but write is 0. They can be read-write, which means that R is 1 and write is 1. They can be execute, which means that R is 0, write is 0, and execute is 1. They can be execute read, so then read is 1, write is 0, execute is 1. They can be execute read write, so that means all 3 bits are set to 1. And then this is funny, Windows lets you set a page as no access. That means that a page can be valid and present, but not accessible. If you access a page that's not accessible, your program crashes. I don't know why Microsoft even has this. I'm not really sure what it's there for. I suppose there's some people who can make good use of it, but it lets you allocate a page. That means the page is valid. It'll be valid and present. It'll be allocated in physical memory, but for some reason your program's decided that nobody should use that page. So you can mark it as no access. Okay. So pages can be marked no access even though they're valid and present. I have no idea, for example, if Linux has a feature like that. Okay. All right. Now your program is going to implement, see, these 8 instructions here are the 8 cases down here that you have to implement. So you have to implement reserve a region, commit a block, touch a page, lock a page, unlock a page, create a guard page, decommit a block of pages, release a region. Okay, so you have to implement those. Okay, you implement them, and this describes, when you read the page, it'll tell you what functions you need to do that with. You use a couple Windows functions to do these things. To go back to the web page, at the bottom, I list some of the functions. These are the functions you want. There's a alloc page that allocates. This is the function that allocates pages. There's a free page. This is the page. This is the function that's going to deallocate pages for you. Okay, and then the lock and unlock. There's special functions for lock and unlock. So these 2 commands here, lock and unlock, have their own functions just for them. Okay, so reserve and commit are virtual alloc. Decommit and release are both done by virtual free. And the lock and unlock each have their own function, virtual lock and virtual unlock. Okay, and touching a page doesn't need a function. That's just reading the page. You'll touch a page by just referencing a byte in the page, either read the byte or write a byte. So you don't need a function to touch a page. It's just, you can do it yourself. You just dereference an address in the middle of the page. Okay. Okay. All right. So you'll implement each of these guys with a function call to one of these functions, one of these functions here. Okay. Every one of these will be written as one of these function calls. And you have to read the documentation of these functions, learn a little bit about how they work. Oh, and real importantly, in this file, I make a blatant copyright violation and give you some pages from a nice old book to describe this stuff. So this is 8 pages from a pretty old Windows programming book that does a nice job of describing the virtual memory functions. Read these 8 pages. They give you little code examples. It's very nicely done. I always thought this was pretty well written. So I just, I scanned these pages in from the book and I made a PDF of them. It's very self-contained. You should be able to get what you need out of these 8 pages. Okay, and then also combine them with the Windows documentation. So combine those 8 pages with reading the Windows documentation, and you should have all the information you need to write the code. Okay, he does. See, this is just the function prototype. So that's just straight out of the Microsoft documentation. What's nice is he gives you some sample code. Yeah. So you can kind of read the sample code a little bit and see what it looks like. Okay. Okay. So print those pages out or just read them, but make sure you use that reference. It's in the zip file for the homework assignment. Make sure you make use of that reference. Okay. Now, there's a demo version of this program in here. There's the demo version that lets you execute the program. Okay. So now here's another program in this folder that I wrote that you're gonna make use of. When a program is running, you'd like to be able to see its virtual memory space. So this is a professionally written program that lets you see the virtual memory space of a program, and this is a program I wrote that gives you a simplistic view of virtual memory. Here's how it works. Okay. For example, I'm going to look at the virtual memory of my TextPad. I want to look at the virtual memory of TextPad. So I open up a command window here, and I type the command vmmapper.exe. Then I need to give the PID of TextPad to vmmapper. So vmmapper can go get the virtual memory space of this program. So I go to Task Manager, and I go to Details, look up TextPad, get his PID, 47024. 47024. Okay? And there is the virtual memory space of TextPad, which right now it doesn't look like TextPad has very much loaded into virtual memory space. This region of virtual memory space is free, okay? And TextPad has got a little bit of data in use. See, this range, at this memory address, there's a big chunk of free memory. So that's memory that's not allocated. Then at this memory address, there's a small chunk of committed memory. Then there's another empty space. Then at this address, there's this size of memory, and then there's more free memory space. Now this is kind of weird. I'm not sure why TextPad showed up as very little memory. Let's look at another example of a virtual memory space. Let's look up the virtual memory space of this CMD program. So go over here to Task Manager and look up the CMD program. It's process 22732. 22732. Oh, I know what's wrong. vmmapper, we're doing everything using 32-bit programs. We're actually running, everything we're running is a 32-bit program. But these are actually 64-bit programs. And vmmapper does not know how to read a 64-bit program's virtual memory space. That's why it's giving me weird answers here. Okay, I should run a 32-bit program. Okay, so I don't know if there's a 32-bit program running here. I'm trying to remember if there's any 32-bit programs on Windows. There's a lot of Word is example of a 32-bit program. Let me see if Word still is a 32-bit program. Okay, here's Word running. I have no idea what this is. Okay. You can see I don't use Word very often. Jeez. This is why I don't use Word very often. Okay. Okay. Well, okay. Oh, Word is running. Okay, it really is there. Okay. Let's see if Word is a 32-bit program. Actually, I don't even know what Word is called. I don't know. Oh yeah, see, it's 32-bit. See, Word is a 32-bit program. Now let me find its process. Oh, they used to let you jump to the process. Okay. Oh, there it is. Okay, it's WinWord. It's actually called WinWord. Okay, that's process 43340. Four, 3, 3, 4, 0. Oh, and it's too complicated a virtual memory space. Okay. So it's too complicated a virtual memory space. But here's what it looks like. Here's the virtual memory space. Okay. So see, what this is doing is it's going through from 0 up to the top of virtual memory space. It's going through the 32-bit virtual memory space. So that's actually, it's not 4 gigabytes. It's only 2 gigabytes because in Windows, half of virtual memory space is given to the operating system and half is given to your program. And you can see that virtual memory space is chopped up into a massive number of pages that are just all kinds of allocations. So Word is a fairly complicated program. It probably has thousands and thousands of pages allocated to it. And you can see that this program is mapping them out, okay? It's showing you at every address how many pages are in use at that address. Free means that there's a region of virtual memory in our picture that we were drawing a while ago. Free is this. See, that's a free region. In virtual memory, I don't have anything at those addresses. Here's another free region. Then these regions are all allocated, but maybe in different ways, because each of those regions has a different set of bits in the page table entry. Over here, this last column tells you things like what it has to do with, like this page is read write, this page is read only. Here's a read write page. Okay, here's let's see, here's a no access page. So Windows really does use no access. Okay, so you can see that here's a reserved page. We have to say what reserved means. Reserved is something that Windows has that Linux doesn't have, and it's not really described in here. Reserved is kind of an odd idea, but Windows makes use of this idea of reserved memory. So for every page in memory, this thing is showing you the status of the page. Okay, so that's a memory mapping program. Now, in this folder, there's another memory mapping program. Here's another memory mapping program. If you run it, it does the same thing as the one I wrote. Instead of giving it a PID, it gives you a pop-up list and says, what program do you want the virtual memory of? So let's do Word again. Okay. There's a fancier way of giving you the virtual address space of Word. You can see it's really huge. Word has got a huge number of pages allocated to it. This thing color codes the pages. It tells you a lot about all about the different kinds of bits that can be set in a page table entry. This gives you a huge amount of information about virtual memory. Okay, so this is a professionally written virtual memory program, but you can use both of. You can use the professional one or the one I wrote. The one I wrote is a little bit easier to use. It's actually for this homework assignment. It's a little bit easier to use it. Okay, now when you run the demo program runs the mapper and maps itself. So this is the virtual memory space of this program. This program is going to let me type in commands to allocate and deallocate virtual memory, which I can then watch happen over here. Okay, so for example, here's some free memory at address 20480. There's an address. That's a hex. I'm sorry. Here's some free memory at address 200000. Okay, I'm going to allocate some memory in that free area. So here's a command. This is an example of a command. I just asked Windows to reserve some memory for me at this address here. See how I just reserved memory at address 2000, and I reserved 65,000 bytes of memory. That's 8 pages. Okay, now reserved means I've set it aside for me, but I haven't allocated anything yet. To allocate a page of memory, I use a different command. In this system, it's going to be the command is going to be to. So now I'm allocating an actual page of memory at 20000. Okay, so hit enter. And now you see there's one page, see 4,000 bytes. I've allocated, Windows calls it committed. So I've actually got committed one page there. Then I've got 7 pages on reserve. So I've got 1 page committed and 7 pages on reserve. If I want, I can allocate another page by going here. This would be the page right after this one. See 2100 is the next page after this one. I'm going to allocate page 2100. Now I've got 2 allocated pages at 2000, and then I've got 6 unallocated, 6 reserved pages starting at 22000. One thing you're going to get very used to when playing around with this program is thinking about hexadecimal representations of addresses. This is going to take real practice. These are hexadecimal representations of addresses. That is a 32-bit address. It's 8 hexadecimal digits. 3 digits is 12 bits, because every digit here is 4 bits. 3 digits is 12 bits. That's 4 kilobytes. So the lower 3 bits, the lower 3 digits in a hexadecimal address represent 1 page of memory. So this column here, this digit here, counts off pages. So pages 0 and 1 are allocated, and page 2 is still on reserve. Okay. Now at commit means that I'm at the status where, let me close Word. Don't need this. Commit means that in the language of what we talked about before, the page has been marked valid but not present. The page is valid but not present. Watch, now I'm going to touch the page and watch what's going to happen. So go over here to Task Manager. I think we have time to do this. One more trick. Go here to Task Manager, go to Columns, select Column, and select the Page Fault and Page Fault Delta columns. The Page Fault and Page Fault Delta columns. Okay. Then find my program in the Task Manager. The program is called VM Driver. There's VM Driver Demo. And here is the Page Fault column. See, now my program is page faulted 137 times. Okay, I'm going to make it page fault one more time now. Okay. I'm going to give it the command to access one of the pages. The command is 3, and I'm going to access the page I just committed. When I hit enter here, you're going to see over here that there's going to be a page fault, because that page right now has been marked as valid but not present, and it's about to be marked present. So I hit enter. Watch over here. See, one more page fault. A page just got marked. A page just got copied into the physical address, the physical memory, and got marked as present. A valid page just got marked present. Okay. If I touch it again, there's no page fault. See, if I keep touching it, there's no page faults because now it's already been brought into physical memory. I can page fault the other page I brought in. So here's going to be another page fault. One more page fault. Bing, see, one more page fault, and I have one more page fault in there. Okay. All right. So we run out of time. Play around with this, and if you have questions, send me email, and on Monday we'll play around with it some more. We'll keep playing around with this. It's real important for you to play with the demo program and get a feel for what the demo program is doing. Okay, and then you have to implement it. So you're going to implement the demo program by writing VM driver. And one last thing, when you're writing this program, do it in steps. Get case 1 working and test it. You should be able to do the 1 commands and get them working and watch them work. Then add the 2 command. Don't try to write all the commands and then try to get it working. It'll be a nightmare. Do them one at a time. Get command 1 working, then get command 2 working, then command 3 working. Do them one at a time. Okay. All right. So as usual, I'll put the video up on the website. I'll put this picture that we drew of the demand paging up on the website. If you have questions, send me email, and please play around with this. Play around with the demo program, and watch. Issue commands, read the documentation, issue commands, watch them happen over here. Get used to talking in hexadecimal addresses. It's a lot like using a debugger. If you've ever used a low-level assembly language debugger, this is a lot like playing around with a debugger. It's good practice in getting used to thinking of hardware, thinking of actual physical addresses. Okay, so let's see. Let me remember how to get out of this. So stop sharing. Okay, so I'm going to end the meeting now. So if you have questions, let me know. Goodbye.